And away we go. As soon as I find some decent chalk. Okay. Now, just one essential linear algebra concept that we'll need is the identity matrix. Does play the role of 1 for n by n matrices. So it's matrix I, assuming everything is n by n squared here, such that if you multiply by any n by n matrix A in either order, we just get the matrix A back for all n by n matrices A. So if you're trying to figure out, well, what is the matrix, what should I look like, what entry should it have in order to have this property, if you were to look at the formula for matrix multiplication that we saw last time, in essence satisfy this, that this summation of AIK times the KJ entry of this identity matrix must be equal to Aij, no matter what the entries of A are. This has to be true for all n by n matrices A. So, so certainly that should mean that the entries must be equal to 1 if I is equal to j and 0 otherwise. And this is a good time to introduce a very helpful notation. This is abbreviated as a lowercase delta ij. So this expression here, this has two indices. It's equal to 1 if the indices are equal, 0 if they're not. It's called the Kramer delta. Because it's fairly common, but you need to have describe some expression this way as being 0 all the time except under a certain circumstance. So I'll be using that from time to time. So this is how we define the identity matrix, and the way I can describe it visually is along the main diagonal, all ones, and then zeros everywhere else. So I'll use a large zeros to convey that it just have a whole sea of 0 entries in certain parts of a matrix. Now, another way I can describe identity using something I did last time is a column partition. So I can describe identity in terms of its columns, and the columns are these standard basis vectors for Rn that I introduced last time, because each one of these, like EI has a 1 in the ith position and 0 in all other components. Or I can describe it as a row partition. So first row, second row, so forth down to the nth row. Okay. All right. Now, as long as I'm bringing up the standard basis vectors, here's another kind of notation that I'll be using very frequently. And that is, what happens if you have a given matrix and you multiply on the right by one of these columns, or if you multiply on the left by one of these rows. So, well, let's suppose I let A have a column partition. So it's n columns. In this case, it doesn't matter how many rows it has. So what will happen is, if I multiply on the right by the J standard basis vector, EJ, then in terms of this column partition, if I write out what EJ is, there's a 1 in a J position, wherever J is, and then zeros everywhere else. So what's going to happen is, as we compute this matrix vector product, I'm going to be going across each row, multiplying corresponding entries by these entries, and adding them all up. But I'm going to keep multiplying entries of each row by 0 until I get to the jth column. So each element is going to come from only the jth column. So what I'm going to get is just AJ. So multiplying by EJ is a way of extracting column J of your matrix. So AEJ is always equal to the jth column of A. Similarly, if I multiply on the left by EI transpose, then that is the ith row of A. So finally, if I put the two together, EI transpose AEJ, well, you take AEJ, that's the jth column. Now I'm taking the ith row of that column. So if I'm taking one row out of a column vector, that's just going to be one element. So what is this going to be?
AIJ.
Yes, AIJ. So this is a convenient way to represent individual entries of a matrix in terms of products involving the entire matrix. So this is something. So this is going to come up again and again. So it's important to get used to. Okay, that actually wasn't even in the notes. That should be in here though.
So just get used to it. I'm just kind of throw that in there like that.
Yes. Okay. Just so it's clear what I'm doing.
It's like on the side, like, so get used to it.
Well, that's really what these first few. That's what this review is. It's all kinds of things to get used to.
Get used to it. I'm gonna start using that.
Oh, like on your students or something? So.
My college professor said just get used to it, so just do it. Get used to it.
Yeah, it was going to be a fun class. Okay. All right. So, you remember from what joy you had when you took modern algebra, dealing with groups, and you had closure and associativity, and then the identity and inverse properties. So now we have an identity element for n by n matrices, so now we can use that to define inverse. Okay. So let's assume that A is n by n. So if there exists, and it does not necessarily, an n by n matrix B such that you multiply B with A in either order, then you get the identity matrix. And B is the inverse of A. And we write that B is A inverse, just like same notation we use for reciprocal. So you can think of it the same way. Okay. Now, we don't need that anymore. Okay. And if this inverse exists, we say that A is invertible. We also say it is non-singular. I remember this actually came up, this issue of terminology, I think it was when Dr. Chen was teaching 326, and he had defined this and explained, okay, inverse exists, but it's invertible. And then later he used the term non-singular, and he had not mentioned it before, and they're like, what does that mean? So put all the terms out there at once. Okay, so and naturally, otherwise, if an inverse does not exist, then we say the matrix is singular. Okay. I should write that down. Now, the inverse gives us a nice way to describe a system of linear equations. So suppose we have a system of linear equations I've described before, ax is equal to b. I can multiply, so if a is invertible, so I can multiply both sides by that inverse that we now know exists. And then on the left side, the A inverse and the A cancel out. So I get x is equal to A inverse times B. Okay. All right, so at least we have a way of representing the solution, but that does not mean, and this is something I'll get into more later at the appropriate time, that it does not mean that we're going to actually explicitly compute A inverse. In fact, it's sort of like a law of numerical linear algebra that you never, ever, 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 ever explicitly compute A inverse. Okay, so now and then I'll violate that, but almost all the time you do not. It's not really an efficient way to solve a system of linear equations. Okay. Now, what I can do is I will describe how you would go about computing the inverse. If you already have a way of solving system linear equations, like you learned in 326, like using Gaussian elimination and substitution, you can use that to compute the inverse. All right. So, so if you look at this equation, A times A inverse is equal to identity. But we consider this matrix equation only one column at a time. So I'm going to let A inverse and give it a column partition. B1, B2, up to Bn. So this equation, I take each column, and what we get is A times the jth column of the inverse, which is Bj, and that is going to be equal to the jth column of this, jth column of identity, but that is Bj. So you can describe each column of the inverse as satisfying this system of linear equations. So really, computing the inverse explicitly, if you were going to do that, it amounts to solving n systems of equations, which can be very expensive. And then once you have the inverse, then you can solve other system linear equations very easily, but chances are it's not really what you want to do. In terms of, later we'll get into the actual cost in terms of how many operations you have to perform, arithmetic operations, and it's generally it's not worth it. Okay. All right. Now, if you were to use a process for solving a system of equations like this, like you learned in your linear algebra course, you do Gaussian elimination and substitution, if a process were to break down, like you end up having a system of equations that's inconsistent or end up dividing by 0, then if it fails, that's because the matrix is not invertible. If a matrix is invertible, then performing those row operations, like row interchanges or adding a multiple row to a number, that will always succeed. Okay. Now, the inverse has certain properties. Some of these will be reminiscent of properties that we saw for the transpose last time. So first of all, the inverse is unique. If you're really, really bored, you can try proving that. Like if you assume that there are two inverses, you can use the properties that we've seen up to this point to show that the two must actually be equal. Also, if A is invertible, then A inverse is also invertible. If you take the inverse of the inverse, that just brings you back to the original. We saw something like that with a transpose. Also, the inverse of a product of invertible matrices, so A and B both have to be invertible, is the product of the inverses, but in reverse order. Just like with transposes. Okay, and finally, the transpose of the inverse turns out to be the inverse of the transpose. So if A is invertible, then the transpose is also invertible. So because these agree, so it doesn't matter whether you invert then transpose or transpose then invert, you get the same result. So we actually have one symbol that describes both operations, A minus transpose. So it condenses things a little bit. Okay. Now, to go back to my parallel with modern algebra, you might have seen this when you took that class. GL and N is called the general linear group. And is defined to be the set of all n by n invertible matrices. So those form a group in the usual sense, that they satisfy properties of closure, associativity, identity, and having an inverse. So I'm sure that Dr. Perry or Dr. Kohler, well, I know they have used this in some examples. Okay. Are there any questions about the inverse? All right. Now, okay. Now, there are certain types of matrices that are a whole lot easier to work with. We need to put those out there. Triangular matrices. Okay. Those are various problems we're interested in solving. Solving system linear equations, or also finding eigenvalues. Those problems are solved much more easily for such matrices. Okay. suppose A is n by n. Okay. Then A is, well, the best kind of matrix is one that's diagonal. If Aij is equal to 0 for I not equal to j. So in other words, the only non-zero entries that you can have be A11, A22, and so forth, up to APP, where, because keep in mind it's n by n, so this is not necessarily a square matrix. So P is equal to the minimum of M and N. And these entries make up what is called the main diagonal of the matrix. So a matrix has several diagonals, so this is the one that's running down the middle, and then we also have diagonals above it and below it. Okay. Now, so the next kind of matrix is upper triangular. If Aij, whoops, I totally messed this up,
Yeah, I was. Yeah.
equals 0
Okay.
for
I
I
didn't know
not
if you
equal to
just
j.
wanted to change that one
Like
or
6.
the other one.
Okay.
Oh, yeah, I could have done either one, but yeah.
So this is the definition you want?
Yes, this is the definition I'm going with. That's my. This is my story. I'm sticking with. Okay.
I was about to push it. Wait, is that a bonus point? Oh, you fix it yourself. I was thinking it though. I was totally thinking it.
Well, that'll teach you to say something sooner.
I'm a slow writer. I was getting. Did you notice it?
I just kept rereading it. And I was like, why? This doesn't make any sense. But I didn't say anything either.
Okay, sooner is better.
Have we agreed on like in class on this too? Not yet.
I don't remember if we settled on
This
that.
is running for bonus points.
Hey, I'm good for everybody. I had her back last class. She's on the list. She's the first one on the list. We just gotta get him on board. Okay, you think about it.
I'm working on her. It's just keep going.
Okay.
Think about it.
Because I mean, as soon as we walk out of here, I'm totally gonna forget about this.
We won't forget.
I know.
You won't forget.
Yeah, let's be clear about
I
that.
have a list of like everybody's.
Yeah, Brianna's gonna be like, I fixed something last time. All right, so upper triangular if. Let's see if I can get this one right. Anything is equal to 0 whenever I is strictly greater than j. So what happens is, the way such a matrix looks is, all right, so I'm going to use x's, and this is something I'll do all semester long. I'm going to use x's to refer to non-zero entries, if I don't really care what their values are. So for instance, the diagonal entries are allowed to be non-zero. But what about this entry down here? This is the 2, 1 entry. So I is greater than j, so that must be 0. And then row 3, column 1. So anything further down. And then, so over here, like this is the 3, 2 entry. I is greater than j again. So those have to be 0. So everything below the main diagonal is 0. We have non-zero entries up here. So now you can see why it's called upper triangular. Use my entries are badly placed. So that way, so as you can see, only the upper triangle has the non-zero entries. So with our problems like solving system linear equations or eigenvalue problems, we'd like to reduce the matrix we were starting with to this upper triangular form because both problems are easier to solve for those kind of matrices. And diagonal is even better, but that takes more work to get to that point. Okay, and then similarly, we can go the other way. That is lower triangular. Take Aij, whoops, equals 0. Can't write anymore. For I strictly less than j. So such a matrix looks like this, where you can have non-zeros on the main diagonal, and below it, I want to have more non-zero entries. I'll make it 5 by 5. Okay, and then zeros everywhere up above. Okay. The thing is, when you have a system of linear equations, and you make a matrix of that system, it turns out to be either lower or upper triangular, then that system is much easier to solve in a general case, because in this case, your first equation has only one unknown in it. So you just perform a simple division, and then you can then use that value to substitute down here. Same thing with upper triangular system. Your last equation, trivial to solve. You just perform a simple division, and then you go up from there. Okay. Now, let's see. I want to point out notation I use to describe lower and upper triangular and also diagonal matrices, because when I'm dealing with them, I don't like to write out the terms upper triangular and lower triangular. And yes, I'm writing a ton of things on the board already, and what does it matter? But it's just how I feel. So, so notation that we use on the board. So the matrix is upper triangular. I'll just write that. You get the idea. And then lower triangular. Okay, and then finally for diagonal. And sometimes use something like that. Okay. All right. I should mention, I'll use this matrix as an example. So this, I've already identified as the main diagonal. Now the this has too many entries in it. Okay. What I have here is a 5 by 5 matrix. Okay, I'm going to clean up this 5 by 5 matrix. Okay. Now, the entries that are immediately below the main diagonal, these right here, that is called the subdiagonal. As you need to refer to the other ones, you might call this like the first subdiagonal, then second, third, fourth. But this is one that's often of interest. And then the entries that are immediately above it, that's called the superdiagonal. There isn't really anything super about it, but that's the name that people use.
Excuse me, so no matter if those are 0 or a number, we call it superdiagonal.
Right. Yeah, so it could be a diagonal full of zeros and it's still super. Yeah, this is about location.
So is there a notation for the tridiagonal?
Oh, like that?
Mm-hmm.
You know what? I've never done that.
Like if you did that notation, we would just assume you're talking about like just a diagonal matrix.
Yeah, I think it's too easily confused with that. So, yeah. Yeah, that never occurred to me. Because tridiagonal does come up pretty often. So, I'll think about that.
Okay.
Yeah.
That's not a bonus point. You don't get a bonus point when you come up with that.
I mean, I don't know.
Okay.
said to go this.
Okay. Okay. Let's see. How are we doing on? Oh wow. Okay. All right. Well, I have something much more fun to work with here than what you know. This is definitely not review. So actually, I'm not sure why I put it in this section, but it's here. So. Well, I guess this is something I do cover in 461, 561. Okay. All right. Um, So there's an interesting formula. If you know the inverse of a certain matrix, the matrix changes a little bit. How the inverse changes. Okay. So suppose I have a matrix A that I already know the inverse of, and I change it to get a new matrix B just by adding this outer product to it. And I talked about outer products before. So this could be used like to change one entry, for instance. Okay. And this is called a rank 1 update. So what I can show you is that the inverse of a rank 1 update is a rank 1 update of the inverse. The question is, what is the actual update? Okay. So the problem is, how to get B inverse from A inverse? And I could just drop a formula on you, but I always find it a fun exercise to derive it. Okay. So let's suppose that X satisfies this system of equations. AX is equal to U. Then, if I go to compute Bx, so Bx would be, so fill in what B is, A plus UB transpose X. But then AX is equal to U. And then I have plus U V transpose X. Now what gets interesting here about outer product matrices like this is when you take an outer product and you multiply it by a vector, what you get is an inner product right there. So V transpose X, that's just a number. And because it's a number, I can move that around. So I can write this as U plus V transpose X U. But the point is, really, I can factor a U out of this. So this is the same as 1 plus V transpose X, that's just a number, times U. Okay. Now, how does that help me? Because I can then get two different expressions for X, because from this equation, I can say that X is equal to A inverse U. But from here, I can multiply both sides by B inverse, and I get, all right, so X is equal to 1 plus V transpose X times B inverse U. And then what I can do is now that these are equal to each other, I can, but this is just a number, I could divide both sides by it. So I can say that B inverse U is equal to 1 over 1 plus V transpose X times A inverse U. And then finally, I have an X sitting there, but I can replace the X with A inverse U. Okay, so this tells me a little something about B inverse. It tells me what I'm supposed to get when I multiply B inverse by U. It gives me this. But the thing is, B inverse is an n by n matrix. So knowing how it acts on one vector doesn't really tell me all that much. I need to find out more. But this is one essential property that I need. The next essential property is, suppose X satisfies this equation. V transpose A inverse X is 0. Now it turns out, if we're in an n-dimensional vector space, there's actually an n-1 dimensional subspace, so most of the space, that's going to satisfy this. Because V transpose A inverse, that's just a transpose of one vector. There are n-1 dimensions of vectors that are orthogonal to it. So if this is the case, then if I compute B A inverse X, well, B is equal to A plus UV transpose. And then I multiply this out. I get A inverse X, which is just X. And then I get U V transpose A inverse X. But that's 0. So that wipes out this whole term. And I'm left with X. So in other words, B A inverse X is equal to X. So now I can multiply both sides by B inverse on the left. And I get A inverse X is equal to B inverse X. So these two equations, turns out, tell me everything I need to know about B inverse. So this is how B inverse acts on one dimension of my vector space. And this tells me how B inverse acts on n-1 other dimensions of its vector space. Between the two, I have the whole n-dimensional vector space covered. So I can use both of these to completely determine completely determine B inverse. Now, to do that, I'm actually going to make the problem a little more abstract. And that's to make the notation less cluttered. The idea is, I know something about a matrix based on what happens when you multiply by certain vectors. So can that give me a formula for the matrix itself? And the answer is yes, and it's going to show you how. Okay. All right. So for my more abstract problem, given a matrix C, find a matrix D so that these properties are satisfied. First, you have specific given vectors W and Z, and then you know that dW is equal to Z. So this is like that B inverse U equals all that junk times A inverse U. So it's a sanitization of that property. And then the second property is that dy is equal to cy if G transpose Y is 0. So for all vectors orthogonal to this given vector G, two matrices D and C end up behaving the same when multiplied by both vectors. So this is like that other property, B inverse X is equal to A inverse X if V transpose A inverse X is equal to 0. So what I'm going to do is I'm going to basically give you a dictionary, if you will. What all the entities I have here, C, D, W, Z, Y, G, what do they correspond to over there? So C corresponds to A inverse. D corresponds to B inverse. That's what I'm really looking for. W is U. Z is equal to 1 over 1 plus V transpose A inverse U, A inverse U. So you can see why I'm making simpler notation here. And then finally, G is equal to A inverse transpose times V. Because that means that G transpose is V transpose A inverse that you can see over there. So what I'm going to do is, I'm going to use these properties to find out what D is. And then I'm going to use this dictionary, if you will, to change all the notation back to what I have on the other board. And then I can write down what B inverse is. Okay. So, here's D. D is equal to C plus Z minus C times W times G transpose over G transpose W. Okay. So that matrix magically satisfies all of these properties. So the reason why it satisfies that is, so to check the first property, if I take dW, well, it's going to be CW, and then over here I'm going to have Z minus CW, G transpose W up top over G transpose W below. And then G transpose W's, those are numbers. So they are going to cancel. And then what I have left, CW plus Z minus CW, causing the CW's to also cancel out. And the only thing that's left is Z. And then for the other property, dy is equal to cy, so if G transpose y is equal to 0, then dy is equal to cy, which is what we want. And then for the rest of it, we have z minus cw, G transpose y over G transpose w. But G transpose y is 0, which causes this whole term to disappear, leaving only dy is equal to cy. So that's how we can use an outer product update to have a matrix satisfy these two properties. And actually, it would have been quite a long time ago, probably about nearly 7 years ago when I worked this out. As far as where this comes from, because it does admittedly kind of look like it pulled out of thin air. Okay, not kind of, I did. But the fact that dy is equal to cy on most of the space, that means you know that you want d equal to c plus something. So that's kind of like your starting point. And the question is then what to put here. And you want to make sure that, first of all, because d is equal to c most of the time, you want this to be just a rank 1 update. It's going to be some matrix of a form like UV transpose. And the thing is, the reason why you want this G transpose here is that if you multiply by anything that's orthogonal to G, that whatever you have over here is going to go away. So I've kind of explained why you need to have this piece. and then why you need to have this piece, the G transpose. What about everything else? That's a little bit less clear, but the idea is you basically solve for the rest of what's here by enforcing these conditions, that you want dw to equal z and so forth. So basically by solving for that, that's how the rest of this comes about. Okay. So in fact, and I know I shouldn't do this because I'm in the middle of teaching, therefore my IQ is lower. But just for fun, I want to try this anyway. If I assume, I don't like to pull things out of thin air. D is equal to C plus, I'll call this AB transpose. Actually, AG transpose. Because if I multiply by anything that's orthogonal to G, then that'll be wiped out. So I know that I need this much. The only thing that I don't know is what is A supposed to be. Then property 2 is covered. Property 1 is not. So then I go ahead and multiply both sides by W. And this is supposed to be equal to Z. Okay. So now I have this equation to solve for. And I need to solve for A. So A turns out to be Z minus CW. And then G transpose W, that's just a number. So now you can see where all that comes from by enforcing this condition. All right, so hopefully that's a little less pull out of thin air. All right. Now, we have this matrix D, which is meant to represent our B inverse. So now I need to take this and replace everything in here, C, Z, W, and G, with their counterparts. And then I can write down what the inverse is. Warning, is going to get ugly. Viewer discretion advised. Of course, I basically think of one time when you said you blew your students' minds and there was basically blood spattered all over. Yeah. So it's. Okay. Yeah, those geometry facts are really gonna freak them out. Okay. So B inverse is equal to A inverse plus. So now the next thing I need is Z, which I've written down over there. Times A inverse U minus C times W, which is equal to U. Okay. And then I have G transpose. So that's G transpose A inverse all over G transpose W, which is G transpose A inverse U. And, okay. Now this formula can be cleaned up. For one thing, I can take an A inverse U and factor it out of this. So what ends up happening is after you factor out A inverse U and then you clean up the algebra here, what you end up getting is A inverse U, B transpose A inverse, all over 1 plus B transpose A inverse U. But there's some simplification of fractions, like you're putting things over a common denominator that simplifies things a lot after you pull out that A inverse U. And I don't feel like going through that here because it's not so interesting. So this is our final formula for B inverse in terms of A inverse. And this is called the Sherman-Morrison formula. Okay. So if you already know how to solve systems involving A, then it's very easy to also solve systems involving B. Okay. And there's a generalization of this called the Sherman-Morrison-Woodbury formula. And I assume that this is just a situation where Woodbury came along by himself and built on what Sherman and Morrison did. But yeah, I'd have to check the history on that. So if you have a rank K update, so U and V are n by K matrices instead of just vectors. So what I've done here is just in case K equal 1. Then we have similar formula A inverse minus A inverse U, which is what we have here. And then I have identity plus B transpose A inverse U inverse. So that corresponds to the 1 over this number down here, but now this is a K by K matrix. And then I have V transpose A inverse. So you can see how the individual pieces correspond to this formula here. And the nice thing is, this matrix here is K by K. So if K is much smaller than N, that's a much easier matrix to invert than the original. Okay. So when you make small changes to a matrix, at least the inverse can be updated. Okay. All right, so questions about all that junk? All right. Okay, so maybe this isn't all linear algebra review. Okay. Now, one big difference between regular linear algebra and numerical linear algebra is that in regular linear algebra, there's much more of a preoccupation with determinants. Are any of you familiar with Kramer's rule from a previous class? Okay. Okay. And sometimes I bring it up, but which expresses a solution of a system of linear equations in terms of determinants. Regular linear algebra, we don't really deal with determinants very much, but I will. They can come up now and then. They can be useful. So, say, talk about that for a little bit. Okay. So we have. So A is, this only applies to square matrices. So this is a notation I use. Sometimes the absolute value notation is used also to refer to a determinant. So what we have is, there's different ways of expressing it. I'll just indicate one here. That's actually defined recursively in terms of smaller determinants, where Mij is called a minor of A. And the idea is you remove row I and column J of A. So you start with an n by n matrix, and then you have a n minus 1 by n minus 1 matrix, so you can be determinant of that. And you can expand along any row or column. Here I'm expanding along a particular row. So I is chosen to be any index from 1 to n. So we often teach you to expand along the first row, for instance. Or you can expand along any row as convenient. You can also expand along a column because the determinant of A is the same as that of its transpose. And now this expresses the determinant of the n by n matrix in terms of n minus 1 by n minus 1 matrices. And then if n is equal to 1, then the determinant of that one entry, just a number, is just the number itself. Okay. All right, and we've seen 2 by 2 determinants fairly often. It's quite easy to do. And then it gets really, really tedious after that. I should mention some terminology that if you take this minor and you multiply it by this twiddle factor here, is -1 to whatever power, that's called a cofactor of A. So you can think of in terms of determinant of the matrix being expressed in terms of determinants of its cofactors. So it's sometimes called a cofactor expansion. Okay. But the problem is, this definition means that computing the determinant of A requires on the order of n factorial arithmetic operations, which is just outrageous. Even for like a matrix like 10 by 10, we're talking 3 million operations. Now, we could do much better than that. For a general n by n matrix, it's possible to compute a determinant in the order of n cubed operations, a function that grows far more slowly than n factorial. And when I get to solving system of equations, I'll cover that then. Now, as far as certain properties of interest, okay. I'm gonna fall behind. Oh, maybe not. What? Okay.
She said, she
No.
spelled something,
He was taking advantage of my faulty hearing.
okay. You go.
Oh, well, 35 years of loud, excellent music can't be wrong. Okay. All right, so these are the last pages I have. We'll see how it goes. Wait, I have, okay, 60 minutes. Okay. If any row or column is all zeros, then the determinant is 0. Okay. If A has any two rows or columns that are equal to one another, then again the determinant is 0. Okay. Now, if you have a new matrix A tilde that's obtained by adding a multiple of row I of A to row J, where I is not equal to J, then believe it or not, that does not change the determinant at all. Right. And this is the most frequently used operation among row operations for solving systems of linear equations. It's using Gaussian elimination. So that operation does not change the determinant. Okay. If you swap two rows or columns of A, it then changes the sign of the determinant. Okay. Because row interchange is going to be very important later for solving systems of equations too. Okay. If you scale a row or column by some factor lambda, then the determinant is multiplied by that same scaling factor. Now keep in mind it applies to scaling a single row or column. So what that means is if you multiply the whole matrix by a scalar alpha, then that scales the determinant not by alpha, but alpha to the n, where A is an n by n matrix. So here, this situation, here I'm talking about scaling one row or column. Here I'm talking about scaling all of them. So we're applying that property n times. Okay. Okay, more properties. Okay. Whoops. That would have been disappointing.
It is very disappointing.
I know, you've yelled at your screen many times. Okay. Now, okay, more properties that are very nice for us. The determinant of a product is the product of determinants. Also, the determinant, as I mentioned this from earlier, the determinant of transpose is the same as the determinant of the original. So in fact, that's why certain properties apply to both rows and columns, because if you transpose the reverse extent of rows and columns, it doesn't affect anything. The determinant of the inverse is the inverse, or in this case reciprocal, of the determinant. One property that's really nice for us that we'll take advantage of to make computation of determinants more efficient than it would be using the definition is how you compute determinants of triangular matrices. So A is, I'll take my notation for a spin. It is lower or upper triangular, it doesn't matter. Then the determinant is just the product of the diagonal entries. So basically, if you take a matrix, a general matrix, n by n, reduce it to lower or upper triangular form, which takes order n cubed operations, then you just multiply the diagonal entries together after that, and you have your determinant. Okay. Now, where the determinant is most useful to us is knowing if a matrix is invertible or not. So the following statements are all equivalent. That determinant A is 0 if and only if A is non-singular or invertible. Okay, so I just gave away the third one. That the inverse exists. Also, Ax equals B has a unique solution. And then the final equivalent statement is Ax is equal to 0 if and only if x is 0. A times 0 is going to be 0 no matter what, but this is the only way you can get 0. So that's called the trivial solution. Okay. There are other interesting applications of a determinant that we don't really get into in this class. For instance, the determinant of a 3x3 matrix gives the volume of a parallelepiped that's defined where the edges are defined by the rows. And that's just generalization of, for instance, a formula for area of a parallelogram that can come from a 2 by 2 determinant if it's in the plane. When we get to eigenvalues later, the determinant of a matrix is also a product of all the eigenvalues. That relates to those geometric applications. Okay. Ooh, I have 8 minutes.
Oh boy.
What?
Determinant 0. Is it supposed to be 0 or no?
Yes.
That was the issue.
How long were you guys debating at?
Like a second we were back here and I was like, he was asking me and I was like,
Sooner.
not that long.
Okay. Anyhow. Okay. Long day. Well, yeah, because I normally get here around 9, but I end up scrambling to get here around 8-ish because I forgot I was supposed to have a meeting with our one fellow grad students, Dr. Schroeder. So I heard him and got here. Dr. Schroeder wasn't here. So I did all that for nothing. Okay. So yes, that's why I'm off balance now. Okay. Last item in this intro, before we get to real matrix analysis starting next time, we'll blend the linear algebra and calculus. A differentiation of matrices. Now, if you have a matrix where each entry is a function of a single variable, and then you want to take the derivative of that, then the derivative of that's going to be a matrix. And to get the ij entry of that, well, that's just the same as taking the individual entry and taking its derivative. But there are more interesting applications, like generalizations of the product rule. You tend to be careful with matrix multiplication. So for instance, if you have a product of matrices, where each entry is a function of some variable, then the product rule applies, but A and B, or their derivatives, have to be multiplied in the same order. So you would have A has a derivative of B plus basically A prime times B. So you can't move A and B around or their derivatives. Okay. But otherwise you still have the same old product rule. And one consequence of that, if I let B be equal to A inverse, then that's just going to be the identity in the left side, and of course the derivative of that's going to be 0. But that gives you a way to describe the derivative of the inverse. And it's something that you can obtain from this rule if you are so inclined. So the derivative of the inverse of this kind of matrix valued function is minus A of t inverse, and then you have the derivative of A times the inverse again. Okay. And then another kind of differentiation is when this really gets into multivariable calculus. If you have a function of several variables defined in terms of matrices, and you want to take partial derivatives with respect to the components, there are certain good-to-know formulas that will come up again later also. Okay. So let's suppose that A is n by n, and you have a vector x in Rn. then some handy formulas, gradients. So you have this function, x transpose ax. So that function, you think it's a function of n variables, all the components of x. It's a quadratic form. And actually, you can write it out this way as aij xi xj. Now, since it's a function of n variables, I can take partial derivatives with respect to each of the n components. And those partial derivatives together make up what you know of as the gradient. Now, it's probably been a long time since I took multivariable calculus, but so the gradient of x transpose ax turns out to be a plus a transpose times x. So in the case where A is a symmetric matrix, it's going to be 2AX. So that you can think of the generalization of calculus formulas that you know, like just using the power rule. Because if n was equal to 1, this would be ax squared, and the derivative of that would be 2ax. So it kind of relates to that. Also, a linear function, you just have a dot product. So the gradient of that, this turns out to be b. Because if n is equal to 1, this is a linear function, bx, and the derivative of bx, of course, is b. Okay. So when we get to least squares problem, also the conjugate gradient method of steepest descent for solving certain systems of linear equations, these formulas will be useful for that. Okay. Well, I only have 1 minute left anyway, but I'm done. So I'm not behind yet. Okay, so we'll get into norms and such on Thursday.